Hello and welcome to a video on common source amplifier design. So in this video we will look at the purpose of each component, because if you want to design you need to know what the function or purpose of each component is, some design parameters and specifications, and lastly we will do some design examples and simulations, since this is the best way to learn a new skill is by applying it. Right, so first let's have a look at a common source amplifier. I picked one at random. So first thing is, let's go with the input and output decoupling capacitors. They are so that no DC from external sources can influence our amplifier. Secondly, the gate resistors. They are responsible for the input impedance of our amplifier and biasing our MOSFET to provide the correct amount of drain current, and therefore transconductance and gain. RD is responsible for our gain in general. RS, if it's bypassed like this one, is responsible for that extra degree of freedom when choosing our drain current, so it's more of a bias stabilization resistor. And the secondary one here, which is visible for a AC model, is for gain stabilization. So we have a huge gain but we want to stabilize it to something smaller, we can just add a small source resistor. Right, so typical things to design for is maximum gain, and that's when there is no source resistor present. And a typical for the maximum gain is it's very dependent on the VDD voltage divided by the overdrive voltage over 2. So typically people will not choose overdrive voltage less than 0.2 volts for a maximum gain design like this. So your VDD times 10 roughly is the maximum achievable gain with full output swing. So that is the typical going rate for maximum gain. The 0.2 VOV is that you don't try to bias the transistor too close to a threshold voltage of your amplifier, and to ensure that it is actually on. You can bias with a lower VOV or a lower overdrive voltage like this. So you can do 0.1, but it's not preferable to do that. Okay, then when designing for a specific gain, is you can go for maximum gain and then just add additional source resistor to stabilize that gain. Typically you also try to design for maximum swing, so the voltage across the drain resistor and the voltage drop across the MOSFET to be the same in the DC of the amplifier, so that you can achieve maximum swing positive and negative wise. But it does not have to be the same voltage across the source. So always try and keep these two the same voltage. So IDRD equal to VDS. And always try and do this as far as possible. Then for the input and output impedances, there is 4 options. Maximum power transfer or matched impedances. That's when you pick the load and the input impedance to be the same. This is very easy to do with the MOSFETs for input and output. So maximum power transfer from a source into the amplifier, since you can just choose your gate resistors to be the same as the signal resistor, and boom, you're matched. Okay, so that's for one option, and this will take your gain every time you have a matched impedance for maximum power transfer. That will halve the gain of your amplifier. We'll get to that in the next slide. Also, a very common one is to design for maximum voltage transfer, and we all know that voltage will rather sit across a larger resistor than a smaller resistor. So into the amplifier, the input impedance should be at least 10 times larger than the signal resistor, and out of the amplifier, the output impedance of an amplifier should be 10 times less than the load. That's how we design for maximum voltage transfer. Right. Next, when to use VDD over 2, when to use VDD over 3. So, with a single rail bias like this, only have a resistor and a MOSFET, we choose these two voltages to be the same. So VDS IDRD is equal to VDD divided by 2. When we have a dual rail application, this point will be close to 0 volts. It's not 0 volts. So again, VSS and RS is responsible for the bias. This is a point close to 0, and we can again design for VDD over 2 for the resistor and the MOSFET. Okay, so this minus VSS over RS is approximately equal to our drain current, assuming that our VSS is much larger than our gate source voltage. Okay, so this is 10 volts and this is 1 volt sitting right here. That is much greater, and you're going to choose E12 components in any case to stabilize the gain here. So that current will be off in the end. Right. When you have a single rail and let's say 3 components like this, we always want these two to be the same. If we add the third one, there is the option to have all 3 components have the same voltage drop, so VDD over 3, making RD and RS the same resistor values. But the odd case and more common with a MOSFET is that the voltage here is a much lower voltage. Still, you try to keep these two the same, and your design changes a little bit. That VDS equal to IDRD is VDD minus this VS over 2. Okay, so there is the 3 typical configurations and when to choose VDD over 2, VDD over 3, and the odd case when VS is a different value. Okay, so a common source amplifier in summary, RGG, which is all the gate resistors, would be your input impedance. Your output impedance is your drain resistor in parallel with your output impedance of the transistor, and the gain is just minus GMZ out. If R out is infinite, which is the assumption when you're designing, the equations reduces. Okay, the only difference when adding a source resistor that's not bypassed is it will have this degeneration effect in your gain, which will help to stabilize your amplifier gain. And again, if R out moving towards infinite, the equations will just simplify. Right. Now, loading effects. The total gain of amplifier is the maximum gain of amplifier. Voltage division on the input, voltage division on the output. So for power matching, input and R sig will be the same values, and R load and Z out will be the same values, giving you the quarter of the maximum gain. For voltage transfer, you try and have Z in be 10 times larger than R sig, and voltage transfer out, you try Z out to be 10 times smaller than R load, giving you about 10 over 11 factor for each one of these two. So if you do voltage transfer on input and output, the loading effect is 10 over 11 squared, like that. So you will find that your total gain, loaded gain, and maximum gain will be values that's very close to one another. They will be typically 1 dB difference, where with maximum power transfer you have a 6 decibel difference between the various loading effects. Okay, so let's look at a couple of examples. After each example, we will look at the simulation of it to see how accurate our design is in the end. So first, we should drive a 10 kilo ohm load resistor, VDD of 15 volts, Kn of 10 milliamps per volt squared, and a threshold voltage of 0.5. Okay, specifications. Maximum voltage transfer to the load. Okay, so the output impedance here should be 10 times less than the load. A Vs of 3 volts, so right here we should have 3 volts sitting. An input impedance of 10 kilo ohms, so looking in we should see 10k, so RG1 parallel to RG2 should be 10k's. And then afterwards, after the design, we need to calculate our input and our gains to see how well we designed, and that will make it easier for us to see the results when we do the simulation. And we should assume a signal resistor of 1 kilo ohm. Okay, signal resistor 1k, Z in 10k. This means we are also designing for maximum voltage transfer into our amplifier. Any case, so first thing to do, draw your small signal model, and there you will see that RG1, RG2 is in parallel, giving us our input impedance. You can write down your gain equation. We need the transconductance. So we know the transconductance, or the easier one to use here would be the root of 2knID. Since the source voltage is a different voltage, VDS is IDRD VDD minus VS over 2. Building an amplifier, we assume we are in saturation. So half Kn VGS minus VTN squared. Vs is IDRS and Vg is Vs plus VGS. And these two equations, the voltage divider to give us our gate voltage and the input impedance. These two equations simultaneously will give us our two gate resistors. Right. So our output impedance needs to be less than our load. So 10 times less would be 1k. So let's choose our drain resistor to be 1 kilo ohm. We know that our source voltage should be 3 volts. So our Q point will be coming from this. So VDD, which is 15 minus 3 divided by 2 is 6 volts. 6 volts divided by 1 kilo ohm gives us 6 milliamperes. And there we have our VDS, and our ID. So from this, we immediately have our Q point. Now with our drain current, we can calculate our transconductance. And this amplifier did not specify anything about the gain. So in the end, the gain will be totally dependent on the transistor chosen here. So the Kn value, and that will give us a transconductance of 10.95 milliamperes per volt. Multiplying that with 1 kilo ohm will give us a gain of about 10.95. Okay, so this is not a very large gain amplifier, but it is being designed for maximum voltage transfer to the load. Right, so there is various ways that amplifiers can be designed, and this is just one form of it. Okay, the point of these exercises is to familiarize yourself with what effects each component will have in the end. Okay, applying our saturated current equation, we get that our VGS voltage should be 1.595 volts, and we also need our Vs value if you want to find our VGS value, and 3 volts divided by 6 milliamperes will give us 500 ohms, and you need to choose the E12 value here. So I went with a 560, and I recalculated the source voltage. Since there is a big difference with this big current and the voltage that it will actually deliver, and it can negatively impact your amplifier if you're not careful. So I recalculated this value before finding our gate voltage. Okay, so 3.36 plus our gate voltage of 0.5 give us 4.955 volts. So this 1.6 roughly plus this 3.36, and that is our voltage divider. And we can take our parallel combination as well, and then we have two equations we solve simultaneously, and we get a 15k and a 53k resistor. So analyzing our amplifier quickly, our gain would be 10.95 volts per volt. That's our maximum gain. If we calculate our load, or our load prime, it's RD parallel to our load. That gives us a gain of 9.95 volts per volt. Our input impedance finally will be 10.31 kilo ohms, and that will reduce our total gain to 9.07 volts per volts. Okay, so we should see something close to 21 decibels, something close to 20 decibels, and something close to 19 decibels in our simulation. So let's open the simulation file. Okay, I've gone before this and got all these values out. So our drain current is 5.6 milliamps, VDS 6.28, close to 20 decibels, somewhere in the middle, close to 19 decibels for our GV. So this amplifier do check out with our design. So if we run it, we have a 50 millivolt input. Very small reduction on the input. So there you can see that if this input is about 10 times larger than this is a very small reduction that you have. And then the final output right there is 450, which gives us a gain very close to 9. Okay, if you want to increase this gain just a little bit, you can make this a 1.2 kilo ohm resistor, and that will probably solve most of this amplifier in the end. So there is our drain current. Here is our Vs, close to 3 volts. And if we subtract this and this, we get about 6.28 volts. So our amplifier does check out in simulation to what we have designed. Okay, and if you wanted to design for exact gain of 10 with the Kn value that we had, just increasing this a little bit actually fixed the gain kind of nicely. But if you increase this too much, the drain source will drop and you can't achieve a very large output swing. So just be careful of that. But yes, make this 1K again. Let's look at the AC quickly. So measuring here is our total gain, so 18.85 decibels. We want to see our loaded gain only, make that 1 ohm. That's 19.655. And if you want to see maximum gain, let's just make this a very large resistor value, or you can even just delete the resistor. But I just tend to make it extremely large resistance. And that takes our gain up to 20.5 roughly. And that's it for example 1. Let's move on to next example. Right. Our second example says that we should design a common source amplifier which is loaded with 4.7 kilo ohms and a load of 10 kilo ohms. VDD is VSS 10 volts. Transistor transconductance of 100 milliamperes per volt squared and a threshold voltage of 0.5 volts. Okay, so we need to do maximum power transfer into and out of the amplifier. This means that we should match input and output with a specific gain of 20 volts per volts. Right. Okay, so first, small signal model. What do we know? The input impedance of this amplifier will be our gate resistor. The output impedance will be the drain resistor. And the gain will be minus GMRD over 1 plus GMRS1 parallel to RS2. So these two in parallel, but if the source resistor for the bias is much greater than the source resistor for the gain stabilization, we can reduce this to just GMRS2. We know what our transconductance is, and we have very simple equations for our DC bias right here. So since this is dual and we try and see this point as roughly 0, we have VDS equal to IDRD is VDD over 2, and our source 1 resistor is minus VSS minus VGS over RS1 is our drain current right there. And again, we assume we are in saturation, so we can just use this drain current equation right here. Since our design is for maximum power transfer in and out, Zin is our R6, so our RG value is 4.7 kilo ohms. Z out is equal to our R load, so our drain resistor is 10 kilo ohms, like that. So two resistors, the choice was fairly easy. Now the only thing in the end is we should hope that our transistor that was given or chosen provides enough currents per volt squared to actually achieve the gain that we had. So what happens next is entirely up to the transistor that was chosen. Right. So VDSQ and our IDRD is the same. So that gives us 5 volts. 5 volts divided by 10 kilo ohms gives us 500 microamperes. And if we plug 500 microamperes into our transconductance equation, we get 10 milliamperes per volt. So we can do a quick check here, and if we take our drain resistor and we multiply it with um, our transconductance, our maximum gain of our amplifier is 100. Okay, so 100 is less than 20 volts per volt. 100 divided by 4 is about 25. So we can achieve our um, gain for our amplifier, even with the matched loads and even with the reduction of our gain to make it 20 in the end. Okay, so with our drain current calculated, we can find our gate source voltage. That is 0.6 volts. Calculating our source resistor for this bias is 18.8 kilo ohms, standard value 18 Ks. The AV0 that we should be designing for is a quarter times AV0, so 20 multiplied by 4 is 80 volts per volts. So if we plug in our minus 80 here, we have a transconductance, we have a drain resistor. We can calculate RS2, that gives us 25 ohms. Choose this a little bit, choose this lower, so the gain actually increases rather than decrease. Can go over 27 ohms as well. That will just have a impact on your gain, making it less. And with this being 22 ohms and RS1 being 18 kilo ohms, this assumption that we make is correct, that RS1 is much greater than RS2. Okay, so we didn't need to account for it really in this equation right here. And I think that is all our resistors designed. RG, RD, RS1, RS2, and yeah, that's all 4 of them. Right. Looking at this equation that we have for the maximum gain, VDD over VOV over 2. This is not ideal where this is about 0.2 volts, but you can still use it in the design if it's lower. It's just a bit of a rule not to choose this too close to the threshold voltage. But the overdrive voltage divided by 2 gives us 100 volts per volts. Okay, so we could have seen this before we started designing in the first place, but now we're just using it as checks. So 100 is much greater than 80 volts per volts. It's the check that we had to do here with our GV and AV0 calculation if we have the gain available. Then we can recalculate our maximum gain We find it to be 81.96 volts per volts. So from here to AV, it should be half. So if your load and your output impedance is the same, this should be 40.98 volts per volts. See, there is a 6 decibel difference. And then going with a matched input impedance of Zin being equal to R sig. Look, 6 decibel drop, and this is half from the previous value. Okay, so half, half, half. Right, let's double check our results with our components with a simulation. So again, I took the liberty of extracting the values beforehand. So here is our designed amplifier, and the drain current is 522 microamps, which is close to the 500 that we designed for. Run the transient here, so this is signal is sitting on top of that 520. There is our, this is not quite the zero that we were expecting, so this top value here minus this bottom one gives us a 5.381 volt VDS, which is close to the 5 we were designing for. AV0 of 83, AV of 41, GV of 21, which is very close to the values we designed for. I think even if you make this 27, our amplifier will be very close to the values that we intended in our design initially. So 50 times 20 should be roughly our 1 volt output. Great, so that's the DC aspects. The AC, output here is 26 decibels now. 26.38 initially, but with this 27 came down a little bit. It's 26.38, making this 1 ohm. The gain should double, 6 decibels up. Make this 10 meg. The gain should double, 6 decibels up. Okay, and there is our amplifier maximum gain, and see, even in transient we get out quite a lot out of our amplifier. So 50 milli-in, but without the loading, this amplifier is going into the triode region right here. So it would be best to actually decrease the input, and you can also see that it's now half again, but it's not in the triode region anymore. But yeah, that is our second amplifier. Let's go to our final example. Our final example is a single rail application with some stabilization for gain and bias. And we should design using a transistor with a 1 amp per volt squared transconductance, threshold of 0.5, VDD of 18 volts. We divide this by 0.1, we get the maximum gain for our amplifier. This is when using VDD over 2, so without the source resistor, we should be able to get a gain out of our amplifier of about 180. which is much greater than our GV of 30 volts per volt. Um, we should design for maximum voltage transfer into and out of an amplifier. So again, input impedance should be 10 times larger than the signal. Output impedance should be 10 times less than the load. Right. So if R sig being 1.5 kilo ohms, the input impedance needs to be 15 Ks, and R load being 33 kilo ohms, the drain resistor here should be 3.3 kilo ohms. Okay, but let's look at the small signal first. So Zn is the parallel combination of these two resistors, bringing us to the design equations for our input impedance and our gate source voltage simultaneously. Since we have a resistor that's not bypassed in the end, again we have a degeneration effect, and we don't have any information on what Vs should be, so the best choice is just to choose all three the same value, so VDD over 3 volts. And those are the design principles for this amplifier. So choosing our resistors, RD will be 3.3 kilo ohms and Zin should be 15 kilo ohms in the end. Dividing 18 volts by 3 gives us 6 volts. So that is to satisfy our three voltages being the same. So RD and RS should be the same value, it's 3.3 kilo ohms. And from this we can calculate our drain current at 1.82 milliamperes. Calculating our transconductance is 60.33 milliamperes per volt. That gives us a gain of about 200 in the end. In any case, moving on, our GV should be our AV0 times these two voltage dividers. If we choose our Zin to be 15 times larger and our output impedance to be 10 times smaller, we will find that our maximum gain we're designing for is 36.3 volts per volts. Right, so that is 31.2 decibels. Now our final design is only to be 30 volts per volts with our loading effects added, so our GV. So with maximum voltage transfer, this is very close to our final value. Right, calculating RS2, we find it to be 74 ohms. Choose it downwards just to increase the gain a little bit to compensate for any other design imperfections. That's 68 ohms. That is our input output, just our stabilization resistors and our gain stabilization, yes, designed. Then we can go and calculate our gate source voltage. That ends up to be 0.56 volts. And our gate voltage in the end should be 6.566 volts. With our gate voltage known and our input impedance known, we have two variables, two equations we can solve simultaneously, giving us a 39 and a 22 kilo ohm resistor. And then we can actually calculate what we should be seeing in our simulations. So this gives us 39 volts per volts in the end with the RS2 that we chose. That is slightly higher than with this 56 at 51.38 decibels. With our input impedance being close to 15 kilo ohms, that gives us 35.5 volts per volts, and decreasing it with our input, 32.26 volts per volts. So now the last thing we can do is verify our design with a simulation. So in our simulation, I took the liberties again of getting these values out. So 1.8 milliamperes for our drain current, 6.14 volts for our VDE value. I didn't change this. Sorry, there you go, it's fixed. This was from an old common emitter amplifier, any case. But 1.8 milliampere, 6 volts roughly across here, and our end goal was about 50 volts per volts for our GV. So I think we kind of achieved our design. So let's run the simulation. That's at roughly 1.8. That's at 12 volts. That's almost at 6 volts. So we have 6 sitting across the transistor here. 100 millivolts in. Stays almost 100 and gets multiplied going out of amplifier. So 50 times 100 milli is 3 volts. So this is very close to the 3 volts that we wanted. Let's look at the AC. Right. So here we have 50.25 dBs. If we decrease this to 1 ohm, stays very close. And if we increase this to, let's say, 33 megs, it should also remain kind of close, 32 decibels. Okay, so this amplifier is designed for maximum transfer, voltage transfer in and out of the amplifier. And that is it for common source amplifier designs. Thank you for watching and see you in the next video.